This is a flip video about polar versus nonpolar molecules. So first it's important to kind of start by reviewing a little bit, and that is in this video we're actually looking at the polarity of a molecule, an overall molecule, versus the polarity of a bond. So if you remember, we've already discussed bond polarity, so let's review that really quickly. I can quickly look at an element bonded to another element seen here, hydrogen bonded to chlorine, and ask this bond right here, is it polar or nonpolar? And if you remember, I can use electronegativity values. There's a chart I can look up these electronegativity numbers. And if the numbers are not equal, then there's uneven sharing. So electronegativity is basically showing an atom's ability to hog electrons when bonded. So chlorine does a better job of hogging electrons to itself than hydrogen. So its electronegativity value is going to be higher. And if you remember, this is called a dipole moment on top here. What a dipole moment does is it's an arrow with a little positive tail. The arrow points towards the more electronegative part, meaning the part of this bond that is hogging the electrons, that is somewhat more negative. The tail, which is positive, is on the other side, which is the other part of this bond, and it is slightly more positive because the electrons are being pulled away from the hydrogen. Not completely, but so it's an uneven sharing of electrons. So that is our old stuff. What we're doing today is we're focusing on the polarity of a molecule, the overall molecule. And when you look at the polarity of an overall molecule, you not only have to look at its bonds, but you have to look at how it's pulling and pushing on those electrons. Okay? We're going to do a much more simpler version of polarity of molecules, and there is definitely more complex ways to do this, but we're going to take this in a very, very simple way of looking at it, and that is basically comparing it to tug of war. Okay? So in this tug of war, we're going to have Miss B versus the sumo wrestlers. That's who's going to be in our tug of war. Okay? So something just really, really simple. So if I was to say, let's just take a look at Miss B and the sumo wrestler in this game of tug of war. Well, clearly the sumo wrestler is going to beat Miss B, even though Miss B is very strong, because he has more ability to pull the rope closer to him. In other words, if we're looking at a bond here, right, and an overall molecule, all of the electrons are being hogged by the sumo wrestler. So if I was to draw this dipole moment, it would go like this. Okay? Now, let's actually start looking at some of these molecules. So I'd like to start off with carbon dioxide. You've already seen carbon dioxide shape. It is linear, seen here. Okay, so if I'm in the middle, and we'll say these sumo wrestlers are fighting over me, so here we go. What happens here? Well, sumo wrestler here and sumo wrestler here, they both have the exact same bodies, the exact same strength, and so clearly they're going to hog the electrons away from me, and so is this one. And they're going to do this with the exact same strength. So what happens? Well, their dipoles are the exact same and pointing in opposite directions. So they cancel each other out. So they cancel their dipoles because they're equal in opposite directions. So they're equal in opposite directions. When this happens, we call this overall molecule nonpolar. Nonpolar. An even sharing. In other words, an even pulling. Right? If we're going to look at tug of wars. This guy pulls just as much as this guy does. So both of them have equaled out. Okay, how about this molecule, BF3? Seen here. Okay? And if you notice, the shape is trigonal planar. So I've got Miss B in the middle. And now I have 3 sumo wrestlers fighting over me. Well, if you notice, this sumo wrestler pulls just as much as this one and this one, right? They're clearly pulling harder, so they're more electronegative, leaving me a little bit more positive. But notice this one is on an angle, and this one's on an angle, and this one's going up. So what happens here is all of these cancel each other out. The 2 on the angle end up canceling the 1 going up. So they cancel each other out, all the dipoles, in opposite directions. So once again, this ends up being a nonpolar molecule, an even pulling. These 2 on the angle even out the 1 above. Okay, now for our last one, we've got water. Now we've got a little bit of a more unique situation here. We have Miss B in the middle, and we've got sumo and sumo. But something a little different, Miss B has some superpowers. Her super lone pair is around her center. Lone pair around her center. And these superpowers make Miss B very powerful. Very, very powerful. So Miss Barazian, just like oxygen, is going to be more electronegative. It's going to hog more, thanks to her superpowers. But these 2 lone pairs, while make me a little bit more electronegative, these sumos are still pulling. And so what we have is we have uneven pulling seen here in water. Uneven tug of war. Uneven pulling. I'm pulling with my superpowers, but these sumos are still pretty powerful. So even with my superpowers, I can't do it alone. So these 2 guys end up pulling a little bit as well. So this uneven pulling makes this overall molecule polar. Okay? So basically what's important is to kind of look at the overall pushing and pulling of what's happening. And obviously, clearly in this instance, these lone pairs made a difference. So this is going to be our overall explanation. It's important to understand the concept and these examples specifically.